So, last class what we did was that we started doing this problem. If you look at it over here, you will find that this is a typical Bénard convection which we already covered, and now we have put a partition which basically suppresses the Bénard convection at the top and the bottom, right. So, it essentially translates to that your Rayleigh number must be less than 1708, right. So, this partition basically freezes the convection on both sides. So, under this pretext, okay, we are supposed to do the problem, and we started, and let me just recap and put the numbers in. So, we said that H1 is equal to x h and H2 is equal to 1 minus x h, delta T1 is equal to x into delta T, delta T2 1 minus x into delta T. So, the temperature is basically it is a linear profile because you are having a pure conduction driven problem now. So, this is basically your, this particular thing is basically your delta T1, this is basically your delta T2, all right. Okay. And this is basically the division. This is H1, this is H2, okay, and this is the partition, okay, and this is the total H. Okay. Now, our objective is to determine the optimal location x, which is basically the optimal location, okay, so that the regime of pure conduction extent, that regime of pure conduction can be achieved for highest RAH. Okay. So, basically the highest Rayleigh number, okay, and Rayleigh number is defined as what? RA G by alpha beta by gamma H cube into delta T, that is the Rayleigh numbers definition, right. Okay. Now, this is the external Rayleigh number based on the overall height, right, and the overall temperature difference, right. Why not actually define Rayleigh number, okay, for this intermediate blocks, for this as well as this, right, because for the partition as for this entire system, each block, that is this block 1 and block 2, they almost behave like independent kind of systems. Well, they are strictly not independent, but they behave like one for the purpose of our analysis over here. So, 1 and 2 basically belongs to, we can define two Rayleigh numbers based on 1 and based on 2, right. So, the idea is that if the individual sublayers do not show any convection, then there will not be any overall convection in the system as well. So, based on this we can write, so as long as the Rayleigh number is small, so G by alpha beta gamma H1 cube into delta T1 is less than 1708. This we know from the criteria of Rayleigh-Bénard convection, okay. For the lower sublayer, okay, so it will be G by alpha beta by gamma H2 cube into delta 2, that is less than 1708. So, that if the convection is suppressed in the entire layer when these two conditions, let us name them as 1 and 2, are satisfied, okay, then there will be no convection in the overall system as well, right. So, in other words, okay, we can substitute, okay, so we substitute the formula for H1. If you recall, H1 was x into H and H2 was 1 minus x into H, right. So, you substitute them over here, okay. So, and we rewrite these conditions as Rayleigh number less than 1708 by x to the power of 4 and Rayleigh number less than 1708 1 minus x to the power of 4. So, these are the two relationships are given. So, this conditions, let us name this as 3 and this is 4. Okay. So, these two conditions are satisfied simultaneously, okay, by all Rayleigh number x points. Okay. Okay. Under, so if we draw now the curve, you will see what I mean. Okay. So, this is your x basically starts from 0, this one is about 0.5, this one is 1, okay. And here we are plotting RA 1708. So, this is 1, this is 10, this is 100. Okay. So, one graph will be something like this. Okay. So, this is 1 by x to the power of 4. The other graph will be like this. One minus x to the power of 4. So, this is the region between the two graphs, okay, in which you have Rayleigh number less than this as well as less than this on both sides. So, these are the two master graphs, right. So, on this side you satisfy one criteria, not necessarily the other. So, in this is the region where you basically satisfy both the criterias, right. So, this is the point, this is the area under the graph, okay, where you satisfy basically the both the things, okay, and this comes exactly as 0.5. So, x optimum is about 0.5, okay, because this is the highest Rayleigh number that you can get, okay. All these regions will be satisfied for any other Rayleigh number. Try to understand that if your Rayleigh number is below these limits, you will satisfy them regardless, but the point is that we want the highest Rayleigh number at which this will be satisfied. So, highest Rayleigh number peaks at around 0.5. Okay. So, you can have lower bounds also, that means you can have x in other locations also, so long as your Rayleigh number is beyond is below a certain value, right. Okay. So, this RAC max, which is the maximum Rayleigh number, is 1708 divided by half raised to the power of 4, which is basically 2.7 into 10 to the power of 3. This is the maximum Rayleigh number that you can achieve, okay, based on this x optimum. Okay. So, what we have done, we have devised two equations, right. We have plotted the two equations. Okay. So, whatever the area is enclosed by these two graphs, right, the area underneath those two graphs is basically the region where these conditions are automatically satisfied. Then you choose the maxima that can happen in that particular region, which is happens at x equal to 0.5, and for x equal to 0.5 you find out what is your Rayleigh number. Okay. So, that is all that we have done in this particular problem. So, this is how you would actually solve it in using the partitions, right. Now, in this light, okay, since we have said for a long time that we will show the Rayleigh-Bénard. So, this is for example a Rayleigh-Bénard convection in a cell. So, this is done using PIV. Okay. So, you can see the two counter rotating cells. So, this is rotating in this direction, this is rotating in this direction. Okay. So, PIV rendition, which clearly shows the flow vectors, right. Okay. And if you go to the following YouTube link that I have marked over here, you can also see that these are basically the Rayleigh-Bénard cells that you create. See this? These are basically the cells. I am just marking them out. Okay. So, you can see the cells very clearly, right. Okay. So, you can see in this kind of cells also you can clearly see that you can see these Rayleigh-Bénard cells, and as you go higher and higher in Rayleigh number, these cells becomes more and more chaotic in nature. Go to this YouTube link to see the full video. Okay. And if you want more quantitative data, these are basically particle image velocimetry data, which basically shows that how the flow actually takes place, okay, between hot and cold essentially, right. Okay. So, hot and cold, and this is of course Rayleigh number is greater than 1708. So, it kind of matches with the problem that we just now did, right. Okay. Okay. So, the problem therefore, it is very easy when I say that there is nothing much to say about it, except that this was the kind of problem that can be easily done without doing much of a math. So, that is the whole point. Okay. Now, let us move to the question number 3, which we kind of said that we will do, right, in the last class, and we did not. So, see, if you read the question, you will find that one way to visualize the y to the power of 4 1/4 dependence of the thickness of the laminar natural convection boundary layer, okay, is to execute this experiment which is shown in this particular figure, right. Okay. So, what we have is that you basically have a vertical isothermal wall which has got a temperature Tw is equal to 20 degrees Celsius, that is the wall. It is placed in contact with an isothermal pool of paraffin. Paraffin is like wax, okay, and the T infinity is equal to 35 degrees Celsius, right. Now, the solidification of the point of the wax is about 27.5 degrees Celsius, right. The solidification point of this wax, which is called as Tm, which you see over there. Okay, so, the wall becomes covered with a thin layer of this paraffin, that is what has happened. So, you have a wall which is at a temperature of 20 degrees Celsius, the ambient essentially is at a temperature of 35 degrees Celsius. This wall is covered with an isothermal pool of paraffin, right. Paraffin, because its temperature lies somewhere between this ambient and the wall, okay, so it naturally freezes, right, freezes and it covers the wall, right, it covers the wall with a thin layer of paraffin, not completely melted, right. And therefore, on the top of this you have the general air flow, right. So, this is the problem, right. Okay. So, this particular problem is used to visualize the y to the power of 1/4 dependence, okay, of the thickness of the laminar natural boundary layer, right, that is the dependence that we have. Now, under steady state, what we have to show is that under steady state condition, the thickness of the solidified layer L, okay, this is the length L, okay, is proportional to the laminar boundary layer thickness, right. That is, it increases in the downward direction as y to the power of 1/4, right. So, calculate L numerically, okay. So, some of the relevant properties are given over here. Prandtl number is 55.9, the thermal conductivity of paraffin is that, okay, and the overall height of the isothermal wall is h equal to 10 centimeter, okay. So, this total height is about 10 centimeter, okay. Now, so the idea is basically to show that the L, which is the thickness of this solidified layer of paraffin, this is the L, okay, basically increases in the downward direction in a similar way as the laminar boundary layer, which is at y to the power of 1/4. So, this is the basic context of this particular problem that we are going to do. So, let us do this. Okay. So, this is question 3, right. So, let q y double prime, okay, represent the local heat flux from natural convection boundary layer to the solid liquid interface, which is maintained at a temperature of Tm, right. This is the solid liquid interface, okay. So, q y double prime is given as kf by y T infinity minus Tm to Nusselt number y, correct. Okay. So, y is measured in the downward direction, okay, in the downward direction. So, we can write that y is measured in the downward direction. Okay. So, the same heat flux, so whatever heat flux is coming from the natural convection boundary layer, the same heat flux should penetrate by conduction to the solidified layer, which has got a local thickness of Ly, right. So, the idea is the same heat flux okay, the same heat flux must penetrate by conduction okay, to the solidified layer of thickness Ly. Okay. So, Qy double prime is basically given as Ks Tm minus T wall by L. Okay. So, what we can do basically we equate these two, this and this, right. Basically you equate those two, because whatever heat is coming from outside has to penetrate the solid wall, right. So, solid layer thickness therefore equal to Ks by Kf Tm minus Tw T infinity minus Tm y by NUy. Okay. So, from table 4.2, which is from Bejan, and Prandtl number is 55.9, that was given the conditions, okay, 4.2. So, you can see that the Nusselt number roughly scales as, or the relationship of the Nusselt number is about by linear extrapolation about 487 into Rayleigh number to the power of 1/4. Okay, this is the same table because I interpolated it between 10 and 100, right, because 55 is right there in the middle. So, you can do some kind of a linear interpolation at that particular stage, right. Okay. So, therefore, or in other words, okay, so L Ks by Kf Tm minus Tw T infinity minus Tm y, okay, then you substitute 0.487 Rayleigh number to the power of 1/4, right. This is just a substitution, that is a substitution that you can do, or in other words this particular thing shows you can do a little bit of more math. L by H will be Ks by Kf Tm minus Tw T infinity minus Tm 1 by 0.487 Rayleigh number H to the power of 1/4 y by H to the power of 1/4. Okay. So, that is the scaling that we have established now, right. So, L scales basically as that, okay, as y to the power of 1/4. Okay. So, the Rayleigh number based on the overall height will be, because that is what we have done here as the overall height, and that was given to us, T infinity minus Tm H cube alpha gamma. So, if you just plug in the numbers over here, it will be 1.39 into 10 to the power of 8. This is still in the laminar regime, which is most of the time that is what we have done. So, L by H, therefore, if you back substitute it over here, this will translate to something like 0.045 y by h raised to the power of 1/4, right. Okay. So, that will be the expression. Okay. So, as you can see, what important concept we used was that whatever heat flux is coming through the natural convection boundary layer, the same heat flux is transmitted through the solidified layer, and we have just equated the two. That is all that we have done, and we have shown that this L is basically proportional to y to the power of 1/4. So, it exactly grows like the laminar natural convection boundary layer. Okay. So, that is the important step that we have taken over here. Okay. So, this completes one of the set. Now, we will look at an interesting problem. So, let us look at the nature of this problem first. So, once again, say you have a bottle of beer at room temperature and you would like to drink it cold and as soon as possible. So, that is the basic statement. Okay. The beer bottle has a height to diameter ratio, that means h by d is approximately about 5, right. You place the bottle in the refrigerator. Okay. Now, you have two options, you can place the bottle vertically or you can place the bottle horizontally, right. Okay. The refrigerator cools by natural convection, that is, does not employ forced recirculation. Which way should you place the bottle? Will it be vertical or will it be horizontal? Okay. Describe the goodness of your decision by calculating the ratio T1 by T2, where T represents the order of magnitude of the time needed for the bottle to reach thermal equilibrium with the refrigeration chamber. Okay. So, this calculation is supposed to be done based on scaling analysis. So, this is not just beer, any other soft drinks that you might have, you always have, if you buy a can, okay, either you can place it vertically or you can place it horizontally. These are high aspect ratio, remember the cans are usually high aspect ratio, that means the height is more than the diameter. In this case it is given as 5. You can have other situations where it can be a lot different. So, it cools by natural convection. So, the idea is that how would you place it, and this you have to justify by taking the ratio of the time T1 and T2 which is needed to cool the bottle down to its thermal equilibrium. Okay. So, that is the problem that we have in this particular case. So, let us look at the solution. Okay. So, this is question 6 for us. Okay. So, the scale of the cool down time. So, one case this is the bottle, this is the can rather, can, bottle, whatever you can think of. The other way is this, right. So, this is your height h1, okay, and g is acting in this direction. This is your height h2 which is placed in the horizontal position. So, this is position 1, this is like position 2. Okay. So, the scale of cool down time. So, first resort to the first law of thermodynamics. Okay, which states that dE by dt, okay, equal to QB to air, okay, the rate of internal energy transport. Okay. So, the cool down time is essentially, so if you convert this equation now, mCb, that is the mass and the, so and this is dTb by dt is equal to minus HA TB minus T air. Okay, where basically A is basically the bottle area. Okay. So, this is basically the rate of change of internal energy is whatever is the heat that is lost, okay, or the heat that is in this particular case dumped. In this particular case, yeah, because the bottle comes to an equilibrium with the refrigerator temperature, okay, and this is mc into b. Okay. So, the cool down time if you write it is T scaling as mcb divided by ha. This from just from the scaling analysis, okay, that a t, if you just take everything to the other side, that is what you are going to get. Okay. So, in other words, so this particular factor, this mcb by a, right, only this part is basically independent of the bottle or the can orientation. Okay. Okay. So, the T1 by T2 is basically a ratio of H2 by H1, right. That is the conclusion. In general, that will be the conclusion. Now, what will be this H1 and what will be this H2, right. So, 1 by H is 1 by H B, that is the bare side, okay, plus 1 by H air, this is the air side. Okay. So, H B here, so there is air and then there is the liquid inside the inside the can. So, 1 by H K R A H to the power of 1/4 B, and H air is given as 1 by H K R A H 1/4 air, right, because both are by natural convection, right. So, the same for the same delta T, because your delta T is basically the same, because your bottle and your refrigerator is kept at the same temperature difference. Okay. So, H B by H air, so it is basically the ratio of the two. Okay. If you take the ratio of the two, it comes out to be around 58.1. So, this means that H B is much greater than H air. So, your 1 by H is almost the same as 1 by H B, right. So, essentially that is the case. Well, I am sorry, let us not go. So, your H B is basically much greater than your H air. So, your H, the overall heat transfer coefficient, is basically therefore H of the air side, right, because it is a 1 by H ratio. Okay. So, this is basically therefore a constant into H raised to the power of 1/4, right. So, in conclusion, your T1 by T2, the time scale, is H2 by H1, which is basically H1 by H2. So, therefore, it is a ratio of the two heights essentially, right. It is 1/4, okay, it is about 5 to the power of 1/4, about 1.50. Okay. So, the cool down in the vertical position requires a time that is 50% longer than the cool down in the horizontal position. So, therefore, if you would like to drink it cold, okay, you should choose your horizontal position, right, essentially. That is all that it means, right, just through simple scaling argument. What we have done is basically you have converted the heat transfer coefficient ratio into a geometric height ratio. That is all that we have done over here by arguing that the HB and H air, that means the HB is much greater than your H air. Okay. So, therefore, the H is governed by the air side, right. So, that is all that we have done in this particular problem. Okay. So, this particular problem is interesting because it uses a simple scaling argument to nail down the same issue. Okay. We have a couple of one more problem to deal with, okay, and after that we will go to the turbulence. See you next class.